Okay, we have a couple presentations now from center collaborators, and the first one's going to be Dr. Nils Volkenborn. A great complement to Paul's presentation, which was on injection well PRBs. He's going to talk about the PRB work that he's really been spearheading during the last 8 years or so, and the great progress he's made towards that. So, Nils, come on up.
Well, really spearheading with lots of other people. Some of them are mentioned here, and I think it's a great time point to talk about this. You heard about PRBs. Now you heard about implementation, all kinds of solutions that we have to address the nitrogen problem. And I hope I can show you that the work that the center has done hopefully will result in the fact that also wood-based PRBs can contribute to solving the nitrogen crisis. And I want to start with a brief statement that even though if we would remove all nitrogen input tomorrow, we will still need to deal with the nitrogen that is already in the aquifer, that we have introduced into the aquifer over the past decades. And as many of you know, maps like this give you an idea about the groundwater travel times. So assuming that lots of nitrogen is already in the ground, over the next, like in red, years, or in yellow, decades to centuries, this nitrogen will continue to seep in our coastal waters. So I want to make the point that, PRBs should not substitute the point sources or in general sources of new nitrogen into the aquifer, but we really should, well, we need to think holistically about how to address this problem. And PRBs should play a role in this, I think, as well as you will later on hear from Mike Dole, bioextraction. So we should do this all at the same time to address the problem. So you already heard about these injection well PRBs. I want to focus on what the center is largely focused on, even though we are getting more engaged also in injection type PRBs. I want to focus on woodchip-based PRBs. And again, like they can last for a long time, 15, 20 plus years. From Paul, we already heard, or you already heard a little bit about the biogeochemistry. It's actually pretty straightforward, and we are specifically investigating to what extent the oxygen that comes with the groundwater, to what extent this is consumed after some period of time, because what we really want to achieve is the complete removal of nitrate, but we don't want to overdo it because eventually systems like this can produce methane, which is a potent greenhouse gas. So one of the critical parameters that we need to figure out is how thick should these PRBs be to get to the sweet spot. Likewise, we are now more and more thinking about column arrays. We already heard about limitation of trench-type systems with these column arrays that effectively can become a trench if you have the right distance. We need to decide, for example, what is the good diameter, what is the type of wood chips we put in, what are the number of rows, so basically controlling the residence time, and all this will be very much dependent on the groundwater velocity and the nitrate concentration at a given site. Our starting point to answer those questions, so what is an optimal thickness, is oftentimes laboratory studies, as you have seen before, column-type studies where we pump water, in this case, bottom up. The nice thing about these studies is you have full control about temperature, the type of media you are testing. You can pump water with different nitrate concentrations at different velocities. And so these graphs here show you from black, the nitrate that we pumped in, to the nitrate then that comes out after about a meter of treatment. I'm not going to the details here. So here we tested different types of wood chips. You see the effluent concentrations can differ a lot between these wood chips. These were 5-year-old wood chips, so they have been already denitrifying for quite some time. So it's really like a long-term performance of this. And as you can see, we pumped here at with different rates, so different hydraulic retention times, or in principle, groundwater velocities. We can also look at the impact of temperature while doing these studies, because obviously all these biological processes are temperature sensitive. So we want to obviously then, when we think about the optimal thickness of the PRB or the number of rows, we need to consider what is the typical groundwater temperature to optimize the design of these systems. And as you can see, obviously, these rates increase as the temperature increase. We also look at what Paul mentioned, the oxygen penetration into wood chip media. We do this by something that we can do in my lab, oxygen imaging. So these are the columns, and the light colors here show you how oxygen is penetrating into the columns at different velocities in these different wood chip types. So it gives us a sense of how much anoxic media we lose at high velocity sites that we need to account for. And lastly, once the nitrate is depleted, as has been true for some of these experimental settings that we used, we see the formation of methane. That's what we expect. That's something we want to minimize. And by having those data, we can actually minimize it. Because what we then use, how we use those data from these column studies is that we use reaction trend, by the way, the concentrations that we measure here are within the range that we oftentimes find in pore water, for example, of salt marsh sediments. Nevertheless, we want to minimize the formation of those. So we then use these data that we get from column studies, and we can inform or parameterize reaction transport models where we then look at different configurations. These are top-down views. We can simulate the flow field because oftentimes these reactive barriers are more permeable than the surrounding soil, at least a little bit more permeable, making sure the water is flowing through them. And then we can add the reaction rates, the oxygen consumption, then the nitrate, the denitrification, and ultimately also the methane formation to come up what would be a good configuration for a given site. In this case here, for example, we simulated a 2.5 foot thick trench, a 5 foot thick trench, and a column array. So we use that information to then inform installations in the field. This, for example, is one site that I'm going to talk a little bit more about. I want to acknowledge Ron Paulson, who was really spearheading this setup together with Molly Graffam. So here we tested basically at one site these different PRB or wood chip configurations in a 2.5 foot thick, 5 foot thick column array. And as a scientist, I also always want controls to figure out what's happening without those wood chips. Just to mention, these have different volumes of wood chips. So comparing these data, please keep in mind that the volume of wood chip that we added in each of these test cells is different. So you cannot just simply compare what the downstream conditions are. And as a scientist, I also want to have replication. So because along the length of this installation, probably the conditions vary a little bit in terms of nitrate concentration. So by having replication, we have more powerful data set to investigate performance. This is how the installation looked like. This is actually an interesting example of where we combined a PRB with the installation of a new bulkhead. These bulkheads are typically totally impermeable, but we would basically use these holes, which are in the subsurface portion of the bulkhead, way below the sediment surface, that allows water to pass first through the wood chips and then through the bulkhead. And Ron really nicely built these cages, so we had really controlled configuration of these wood chips. This is the column array, and here you see the 2.5 and the 5 foot thick PRB trench. After the installation, everything looks like this. It's actually a quite nice place to work at. And we now regularly go there, pump water from upstream within the test cells, downstreams, and do all kinds of work there. It's really a great research PRB setup. And just like I don't want to go into the details of those data here, but what you see here are now data over time from 2021 to 2023 for the 4 different test cells, let's say, the controls, the columns, and the trenches. Blue and triangles mean what we measure up gradient. So in the orange means what we measure in the center of the test cells, and green what we measure down gradient of the test cells. So obviously, not surprisingly, in the control, not much is happening. However, if you look at the columns and the trenches, you see there's nitrate coming in at most of these locations, at most of the times, variable in time, but also depending on location. But what you see that they typically remove all the nitrate. So nitrate here, and downstream we don't measure anything. And that's specifically true for the trenches, where actually the yellow, the middle, the center measurements are hidden behind the downstream measurements because the nitrate is already depleted at the center of those test cells. We also found, as we would expect, when nitrate is depleted, specifically already at the center, we see methane in the effluent. So that's something obviously that we want to minimize. Luckily, we don't. We also took samples in the non-saturated soil above these test cells. There we couldn't see any methane, while we measured elevated CO2 concentration. So we truly got gas emitted from these test cells, but there was no methane in it, meaning there is no outgassing of methane. All the methane that is leaving those test cells is really dissolved in the water. And again, for context, when we estimate the fluxes per area that come out of these 5-foot thick test cells that overtreat the water, these fluxes are actually not far, a little bit higher maybe than some of the reported methane fluxes to the atmosphere measured in salt marshes. So again, like, not super concerning, yet we have now the tools to minimize this. We are currently working on establishing more pilot systems, and specifically these column arrays are really promising because they are easier to implement, they are less intrusive, and you can treat water deeper. So here you see we use a geoprobe. We fill then these 10-inch inner diameter columns with wood chip pea gravel mixtures. And in this case, again, like, we use reactive transport modeling to decide what would be a good distance, giving the groundwater velocity that we expect at the site, giving the nitrate concentration that we expect at the site. Here we decided at Georgia Pond to go with 10-inch inner diameter wood chip columns 36 inches apart, because the model suggested then this will act like a barrier. This is just a pilot study. We choose a flower because this flower basically represents a subsection of a 3-row setup. And just like some first data that we just got are, so in blue you see the wood chip columns. We also can take samples from within the columns, which are shown in red. You see within these columns all the nitrate is gone. But even if you look through the gradient going from top to bottom, here in the upper part you see more like concentrations of 4 to 5 milligrams per liter. While if you go down, you see even some values below detection limits, maybe 1 milligram per liter. So it really suggests that the system, that this array is already functioning for months after installation. And even more, what I always like is, well, we use the model to inform the design. So now we can compare the prediction that we did based on the model with our data. And actually there's a pretty good match. And I'm looking forward to get more data from this system. So this work is not meant to show if PRBs work or not. They work, it's clear. We now, however, also have, we know, for example, for the Hampton Bay site with the nitrate that comes in, we can remove somewhere between 6 and 9 pounds of nitrogen per year per meter of linear footage, which is within the range of what each of us releases to septic tank each year. We now have the data to optimize the design to minimize the formation of methane. And these wood chip columns arrays, I think, are a really promising approach in many sites that we hopefully will install systems. And just like, again, like a cost-benefit analysis like Paul did, obviously depends on lots of assumptions. But again, mostly these data suggest that we are well within the range of all these other technologies, or even like at the low edge of end of these estimates, with maybe $20 to $30 per pound of nitrogen removed. Over, in this case, the assumption of a 20-year lifetime. So the biggest challenge, I think, moving forward is implementation, as Sue mentioned. And in this case, it's really like how we can find and localize suitable sites for PRBs. And luckily, we have the Suffolk County Subwatershed Plan, and there's actually a lot of useful information in there with respect to the, estimated nitrogen concentrations in the shallow aquifer based on current practices. So what we miss still is considering past practices. As we heard from Stuart, it dramatically changed over the last few decades with poultry farms in past decades, and now we have, and since the water is moving slowly, we probably need to consider these past usages to find out where the nitrogen may be and potentially then emit it. But we also get information about current loads and contributing areas to the watershed or to the subwatershed. We have information about groundwater travel times, flow direction, likely end sources. So all this information can guide us to locations where, however this is still needed, comprehensive site investigations are necessary to really then make informed decision if a PRB at a specific site is suitable or not, and how it should be designed. So this is obviously associated with upfront costs. So you need to do this comprehensive site investigation to make the decision and obviously then eventually implement a system. To streamline this process, Sue and DEC and some people here at the CCWT have now worked on a guidance document that will come out later this year, which will hopefully help to streamline this process from finding a suitable site, doing the initial monitoring work, and eventually help with the implementation, which will include information about permitting, and also early on maybe deal breakers where you don't want to invest more time and money into a specific site because it doesn't seem suitable. So the strategical placement of PRBs, I think, should be considered as a really good additional tool in the toolbox in a holistic approach of addressing the nitrogen problems. They must be properly installed, and hence you need some site characterization efforts there. The costs are within other techniques, and we continue to monitor the systems that are already installed at various sites on Long Island. We are in various stages of site monitoring and figure out if and what kind of configuration would work there. And obviously, we will continue to work to identify additional sites with partners and then hopefully secure funding for more work, for implementation of PRBs. Thank you very much.